Welcome to week 12 of the ma161 calculus. My name is Götz Pfeiffer and this video is about exponential growth and decay. Exponential growth or decay is a widespread phenomenon. Many quantities in nature grow or decay at a rate that is proportional to their size. For example, if a function p of time t describes the number of individuals in a population, then one can expect that the rate of growth, which is the derivative p prime of t, is proportional to the current size p of t. In other sciences, in physics, the mass of a radioactive substance decays at a rate that is proportional to the mass. In chemistry, there's the example of the unimolecular first-order reaction, whose rate is again proportional to the concentration of the substance. And so it's not science, it is finance, and the value of a savings account grows at a rate that is proportional to the current value. That's probably something most of you haven't experienced with interest rates being so low, but still it's a model. It applies in particular to continuously compounded interest rates, where exactly the same relationship applies. The growth rate is proportional to the current value. And finally, in a pandemic, a virus at first spreads at a rate that is proportional to the number of infected people. Let's look at the underlying laws and equations. It's sometimes called the law of natural growth or the law of natural decay. So in the calculus setting, we're talking about a quantity y that depends on, say, time in the form of a function f of t. And if this quantity has a rate of change that is proportional to y itself, then we can express this fact by the equation y prime equals k times y for some constant k. Now that's the calculus way of saying that the rate of change of y is the k-fold multiple, is k proportional to y itself. That's an equation. That's an equation which involves y as the function y as an unknown quantity and its derivative. For that reason, it's called a differential equation. I guess you'll see more of differential equations next term. This will be brief. Fact is, even if this is the first differential equation you ever see, we know a solution. We know that the exponential function is its own derivative. So in terms of this differential equation, for k equal to 1, we know that the exponential function is a solution to the equation y prime equals y. Now, the exponential function is such a quantity y, which is its own derivative, its own rate of change. More generally, we know that a function f of t described as some constant capital C times e to the power k times t has the property that it's, this chain rule and all the differentiation rules we've seen, the derivative of this function f with respect to time t is c times k times e to the kt, which obviously is the k-fold multiple of the original f of t. This is a solution to the differential equation y prime equals k times y that we know from this course. In fact, this is the only solution. And again, we have seen in this course the means to justify this claim, starting with the observation that the derivative of the natural logarithm of y, where we still regard y as a quantity that depends on time, so this is the derivative with respect to t of the logarithm of y, is y prime over y. Then we can rearrange this equation, y prime equals k times y, as y prime over y equals k, and then, that's something we learned last week, we can take antiderivatives on both sides. From this equation, which says that the derivative of the logarithm of y is exactly this fraction, we know an antiderivative of the left-hand side is the logarithm of y, ln y. And an antiderivative of the constant k is k times t, which we either remember from last week or you verify this by taking the derivative of k times t, or the derivative of k times t plus a constant d will be k. So we've replaced both sides here by their antiderivatives, and then if we apply the exponential function to this, to solve this for y, we get y equal to e to the power k times t times e to the power d, where I abbreviate e to the d as c, and obviously this constant c is the value of y when t equals 0, the so-called initial value, y at time 0. That's the argument which shows that this function c times e to the kt is the only solution, or these functions with any capital C are the only solutions to this differential equation. That's worth remembering, that we state as a theorem. The only solution of the differential equation y prime equals k times y for a constant k with initial value y at 0 equal to a capital C constant is the exponential function of the form y equals c times e to the k times t. This should be t we had as a variable all the time rather than x. T. Okay, then let's look at this in the context of population growth. We denote by p of t a function that measures the size of a population in terms of time. So p of t is the size of a population at time t. Assuming that the population grows at a rate that is proportional to its current size, we have p prime equal to k times p, where k is a constant, or p prime over p equal to that constant k. This constant k, p prime over p, is called the relative growth rate. And to say that the relative growth rate of a population is constant is the same as saying that the population grows at a rate proportional to its size. And together with this capital C, which is the initial value, the growth rate k completely determines the solution, the model or the function p of t that describes the growth of this population. So if you know the c, the initial value, and the relative growth rate, you know this exponential function that describes the population growth precisely. For example, if we have a population that has initial size p0, at time 0 the size is p0, and grows at a relative rate of 2%, which is the same as 0.02, then p of t is that p0, the initial value, times e to the 0.02 t. Let's make this a bit more concrete and look at the world population. We looked at that before, didn't we? And found that the world population doubles roughly every 50 years. Let's see. On the internet you can find these figures. The world population in 1980 was 4,458 million, and in 2020 it's 7,831 million. To be precise, these are the numbers on the 1st of July, in the middle of the year. Assuming that the world population grows at a rate proportional to its size, let's determine the relative growth rate. Then we'll set up a model for the world population and use it to estimate the size of the world population in 2000 and to predict the population in the year 2050. How do we do this? Well, we measure time in years, and let's say time starts in 1980, and the year for which we have the first data here. So t equal to 0 corresponds to 1980. Then the 4,458 is our initial value, p of 0. And the number for 2020, that's 40 years later, is p of 40. Then, by the theorem we just saw, this exponential model is p of t is equal to p of 0, the initial value, times e to the kt. We're interested in finding the k, the value of k, so let's substitute 40 into this equation. Then we have p of 40 is p of 0 times e to the k times 40, which we can write as e to the 40k equals p of 40 divided by p of 0. And that's the quotient of the two numbers which are given. And then to get at the k here, we apply the natural logarithm and divide by 40. So we get k equal to 1/40 of the natural logarithm of this quotient, which comes out as approximately 0.014085. That's about 1.4% for the relative growth rate of the world population. Now we have an initial value, the p of 0, and the growth rate, and so we can now write down a model for the growth of the world population, or for the size of the world population over time, as 4,458 times e to the power k, this is 1.4%, times t, where we can compute e to the power k explicitly. That gives 1.014185. So we can describe this function as 4,458 times the tth power of 1.014185. Now to answer the outstanding questions, what is the world population in 2000 and 2050? For 2000, this gives p evaluated at 20. So we substitute 20 for the time, and this evaluates to roughly 5.9 billion. If you compare this to the figures that are given on the internet, there it was 6.1 billion. That's not quite a match, but same order of magnitude. For 2050, this gives p evaluated at 70. 2050 is 7 years away from time 0, which we set in 1980. So we substitute 70 for t in the formula, and this gives 11.9 billion. Roughly twice as much as 50 years earlier. Again, confirming this observation that it doubles every 50 years. That's actually true. And we're now, 2020, we're now at about 8 billion. When I grew up, the number I learned was 4 billion. And now, 50 years later, twice as much. Okay, on the decay side, things work similarly. You can find the relative growth rate, and it's just, yeah, for the decay, the relative growth rate would be negative. As a slight variation, I'd like to look at Newton's law of cooling, which introduces a little shift, a little function yoga into the picture. Newton's law of cooling states that a warm body cools down at a rate that is proportional to the difference in temperatures between the body itself and its surroundings. So here, if we denote by capital T the temperature and make it a function of time, little t, let's also denote by T subscript S the temperature of the surroundings, then the Newton's law can be expressed in calculus terms as T prime equals K times T minus S for some constant K. The change of rate of the temperature, T prime, is proportional to the difference in temperatures between the current temperature of the body and the temperature of the surroundings. The constant K describing how this is proportional. And there's this difference rather than T itself in the equation. But that causes us no difficulties. To simplify things, we substitute variables and set y equal to the difference, t minus ts. Then it's still true, because ts is a constant, that the derivative of y is t prime. And so we can solve the equation y prime equals ky for y and get, with the methods we saw before, y described as y0, the initial value, times e to the kt, where k is the relative growth rate or decay rate in this case. And translating this back into the language of temperatures, y was the difference, y0 then again is a difference of temperatures. We get t minus ts is t0 minus ts times e to the kt. As a concrete example, let's take a glass of milk at room temperature, 22 degrees, and put it into the fridge, which has a temperature of 7 degrees. Half an hour later, we notice the milk has cooled down to 16 degrees. How long do you think would it take for the milk to cool down to 10 degrees? Well, let's see. We're given at time 0 an initial value, which now is a difference between two temperatures. So at time 0, the difference between the body, the glass of milk in this case, and the surroundings is 22 minus 7, that's 15 degrees. Also, we're given the information that at time 30 minutes after 0, the temperature difference is 16 minus 7 is 9. So T30 minus the surrounding temperature is 9, from which we conclude that, in the same way as we did it before, substituting the value 30 into this equation, or into this form of the equation, doesn't matter. T is 30, so we get e to the 30k is the quotient of these two differences, which we just determined. E to the 30k is 9 divided by 15, which is 0.6. So again, take logarithms, divide by 30 to get the k. We find that the k is approximately minus 0.01703. Note it's negative. We're talking about a decay phenomenon. temperature goes down. And now with that k and the initial value, we now have all the ingredients for the model, which is the temperature difference is 15 times e to the minus 0.01703 t. And the question is, at what time, for what value of t is the temperature difference 3, 10 minus 7. So again, we divide, so to solve this for t, we divide by 15, take natural logarithms, and then divide by k to find that t is approximately 94.5. That's 1 hour 35 minutes. And that's it for the growth and decay. And in the next video, we're going to apply this kind of reasoning to modeling a pandemic.